Take a single large language model, assign it a system prompt, give it access to a local memory buffer, and ask it to execute a standalone task. It will likely succeed. The baseline works. This initial success creates a specific engineering impulse. The immediate instinct is to scale this baseline directly, wiring multiple agents together through APIs and passing raw, prompt-driven payloads between them to form a multi-agent network. There is a pervasive architectural misconception that scaling these networks simply requires larger context windows or more sophisticated prompting techniques. In practice, as task complexity and agent count increase, coordination breaks down. Agents relying entirely on their own isolated, local interpretations of incoming data begin to fail at basic handoffs. This failure occurs because the network lacks a shared, governed reality. Each agent evaluates instructions against its own isolated context, leading to immediate disagreements about state, identity, and rules. Prompt-driven architectures struggle to support multi-agent scaling. Because each new agent introduces a unique point of interpretation, the system becomes less reliable as the network of autonomous actors grows. Watch these data payloads actively corrupting between isolated agent nodes. This is semantic drift, identical terms interpreted differently across the network. This triggers policy drift. Risk thresholds and rules are evaluated inconsistently. Ultimately, it forces context fragmentation, with agents executing on conflicting assumptions. Traditional software systems can often survive fragmented data. Their execution paths are procedural, hard-coded, and predetermined by human developers. Agentic systems operate differently. They make active selections at runtime. They interpret signals, choose actions, and operate under delegated authority. When execution relies on real-time interpretation, data fragmentation causes catastrophic, unpredictable failures. Without a mechanism to correct systemic drift, every agent added to a workflow compounds the variance in interpretation, driving the system inevitably toward an unrecoverable state. Solving this requires a specific architectural shift. The network requires an agentic data backbone. This backbone integrates databases, data lakes, and vector search into a single governed runtime concept. It serves as the bridge between storage components and the agents that consume them. The backbone is a semantic, policy-linked, provenance-aware data substrate. It is a governed foundation designed specifically for autonomous systems. Instead of agents inferring meaning ad hoc during runtime, meaning is explicitly declared in the backbone. Every agent, protocol, and control gateway draws from the exact same definitions, rules, and historical evidence. It operates not as passive storage, but as the active, governed memory and semantic execution fabric of the entire system. This 3x3 architectural grid maps out the 9 canonical data types required to construct a functional memory substrate. Organizing the backbone into these strict classes stops category drift entirely. First, structural data maps the topology of existing entities and identifiers. Next to it, contextual data provides the strictly bounded situational view an agent needs to act safely in the present moment. Behavioral data captures execution patterns over time. Semantic data locks down definitions and mappings, ensuring a term like approved means the exact same thing to every agent. Trust data embeds identity, authority, and validation signals. Policy data translates organizational governance into machine-consumable constraints and permissions. Policy engines cannot evaluate vague prose. They require these exact structured fields, risk classifications, time windows, and state markers, to enforce rules reliably at runtime. Lifecycle data manages versioning and deprecation. It dictates how event schemas evolve without breaking the coherence of the existing network. Interactional data treats multi-agent handoffs as strictly governed system states, recording commitments, approvals, and escalations, rather than ephemeral chat logs. Finally, provenance data, the immutable, append-only evidentiary record that provides proof, replayability, and audit trails for every action taken. This 9-part taxonomy ensures the system captures the complete coordination, operational control, and proof required for autonomous operations. To see how this architecture dictates behavior, we have to look at a live multi-agent operation. Look at this architectural data flow diagram. A single event packet is entering an agent node. Notice how it instantly triggers a 10-step runtime pattern, firing rapid vertical queries down into the 3x3 backbone grid beneath it. Step 1. The event is received. Step 2. It is strictly matched against explicitly versioned event reference data within the backbone to determine its exact structural meaning. Step 3. Relevant protocol state is retrieved. Step 4. A bounded operational context is assembled from governed sources, giving the agent its immediate reality. Step 5 resolves the acting agent's passport, instantly mapping its identity to specific delegations, scopes, and trust levels. Step 6 is the critical policy check. Constraints are evaluated directly against the structured facts we just pulled from the substrate. Step 7. Only after passing these validations does the agent execute its action. It operates strictly within that securely bounded context. Step 8. The resulting outputs and decisions are generated. Steps 9 and 10. The new interaction states and the immutable proof of the event are immediately recorded back down into the substrate. The agent did not infer systemic meaning. It retrieved declared meaning from the governed foundation, acted on it, and documented the results. This runtime flow guarantees that every autonomous action is legally and technically secured by valid semantics, valid authority, and irrefutable proof. For highly regulated enterprise environments, that final step, provenance, is the dividing line between experimental AI deployments and production-ready systems. This cascading matrix is the mechanism of provenance. It captures an append-only evidence trail of actions and decisions, preserving specific context for every execution. Without an append-only trail locking into place, a multi-agent system might successfully complete a workflow, but the enterprise cannot legally prove why the system chose that specific path. Structured memory provides the exact inputs required for deterministic post-incident reviews, compliance audits, and precise state replays. Provenance transitions the architecture from a black box AI operation into a strictly governable, auditable enterprise memory. This macro view demonstrates an enterprise-wide ecosystem of agents and gateways operating seamlessly across the glowing backbone grid. Attempt to build this without the backbone, and coordination costs rise exponentially. System assurance collapses under the weight of semantic disagreements as the agent count grows. With the backbone, the network evolves safely. Controlled rules and strict data standards allow new policies to deploy without fracturing existing operations. The architecture relies on functional harmony. Ontology dictates existence, semantics dictate meaning, policy dictates boundaries, and interaction state coordinates execution. If engineering teams ignore this foundational substrate, the compounding cost of system inconsistency will rapidly outpace any efficiency gained from autonomy. True, safe agentic scale is never achieved by deploying smarter models. It is achieved by engineering a rigorous, structured memory foundation for those models to operate against.